Okay, none of the stuff before is sort of specific to linear algebra. You can have maps between vector spaces that are not linear, but then you can still look at whether they're one-to-one or onto. But here we're going to do with linear maps. Now, linear maps pay special attention to linear combinations. So there's two properties that are equivalent. One is these are definitions. A map is linear if this property holds f of r v1 plus s v2 equals r f of v1 plus f of v2. So you can sort of like f moves past the sum and the multiplication. So in words, what it says is the image of a linear combination of two vectors is the same linear combination of the images of the two vectors. Right? Here's the images of v1 and v2, and you're starting off with the image of a linear combination is a linear combination of images. So that's just sort of become. Now, this property has to work for every two numbers r and s and v1 for all numbers r, for all real numbers r and s, and all vectors v1 and v2 in the domain. So it has to work for everything in order to work. I mean, it might be that for certain vectors this held, but not all of them. So it has to hold for all of them. Now, this is equivalent to this property, f of v1 plus f of v2 equals f of v1 plus f of v2 and f of s v equals s f of v. Now you can see that condition 1 implies condition 2, right? This first line is just a special case of the other one where I choose r equals 1 and s equals 1. Right? I just saw r equal, that I get this is just a special case of number 1. And the second line also is a special case where I say choose r equals to 0 and s equals to 1 and v equals to v2. So the conditions 2 are just special cases of condition 1. But it also works that if I know that 2 holds, then it holds for every vector v1 and v2, then what I can do is I can say, okay, well, if I start off with the left-hand side here, I can apply this property of f of v1 to I can do it in 2 steps. I can sort of say, okay, if I start and ask, can I get 1? Can I get 1 from 2? It's obvious you can get 2 from 1 because they're just special cases. But here, so I look at this side and I say, well, let's see what the image of this is. Well, I can apply the first bit here to these 2 vectors. So this should equal f of rv1 plus f of s v2. I just applied it to, I can take any 2 vectors and just divide them up. But then I can apply the second one here to each one of these individually to have r f of v1 plus s f of v2. I can factor out the r and the s, and I recover property 1. So they're just 2 equivalent. This is like a proof that I've got 2 different ways of dealing with it. And so if you wanted to prove that a map is linear, you can either do it in sort of one equation, but then you've got like 4 letters, right? You've got v1, v2, r, and s. Whereas here, this is a little bit simpler because you just have v1 and v2, and you can focus on that, and then you can do this. So if you wanted to show a map as linear, you could use either one of these. Okay, it turns out that there's a third thing that's also true. If it's true for 2 linear combinations, it's true for like a linear combination of 10 vectors. If I had a linear combination of 10 vectors, the image will be the same linear combination of all the images. That's just sort of like saying if I take 3 in here, I could use this multiple times and get out And so that's some theorem that says but then, so this is the property of linearity. And last time we looked at specific maps and we checked whether or not how to show that they were linear and one-to-one and onto using those definitions. Okay, and so the thing is that it turns out that there's two sort of big applications. This is a whole structure now, and the question is, what are the applications, or what are the, not applications, what are the consequences? Well, the consequences are the following. Let's say that there's an isomorphism. Okay, well, first of all, I didn't define isomorphism. And isomorphism is a linear correspondence. Okay, well, correspondence is one-to-one and onto. So if a linear, so an isomorphism is a linear map. We're only going to be interested in linear maps. That's also one-to-one and onto. So the question is, what's the consequence of there being an isomorphism between two vector spaces? Well, let's check and say, what if there is an isomorphism between V and W, what do we know about V and W? Well, we know that there's some map. We know if there's an isomorphism, let's just call it F between V and W. Well, now we know that V has a basis, right? So let's consider, so we know because V is a vector space, we know V has some basis with dimension V vectors. It has, because dimension V, let's say with n vectors, and that is the dimension of V, because that's how we define the dimension of V, is the number of vectors of any basis. So we have some basis here, which is like V1, V2, Vn. And in the middle, we're going to put one sort of an arbitrary one, because we want to do something with every single one of these. And so we're going to let this I, we've got I equals 1, I could be 1, 2, 3, 4, 5, 6, 7, n minus 1, and n. So it could be anything. Now, so we have some basis, and we want to look to see the consequences of there being an isomorphism. Oh, did I do the wrong one again? Let's put a page. No, it is a page. Oh, there. No, I did. Okay. Problem here, I sometimes check this when I want to do this, and then I end up a blank page in the wrong place. Okay, so let's look at F of V1, F of V2, F of VI, right? So these are all vectors, like this is W1, this is W2, this is W sub I. So we've got n images. Okay? Well, what is going on? Got some problem with let me. Okay, so I've got n images, and we know F's an isomorphism. So what we want to say is that, well, how many different vectors are there, right? Do we have n? In other words, for a general linear map, some of these could be the same, right? And it could also be, remember that F is onto, right? So because F is onto, let's take, I can check. I want to check the properties and use the prop. So here's the goal. I want to use the properties that F is 1-to-1 and onto. So this is the goal. Use the properties of 1-to-1 onto to show that the WI, the images of the basis vectors here form a basis of W, the codomain, with the same number of elements. Number of vectors. Because then, if that was the case, the dimension of W would be the same as the dimension of V if it had a basis with the same number of elements, right?
So the images of the basis vector form a basis of W.
Yeah, so we've got a basis for V, right? And then we know that there's images. We want to show that these W's, these images form a basis of W, right? We've got a basis of V that has n vectors, and we want to show that these W's are going to form a basis of W, So to do that, we have to show that I can choose any vector in W, and write it as a linear combination of these ones here.
So,
okay.
Sorry, if you could just quickly go over again, what's just the brief definition of images again?
Okay, this is an image. This W1 is image. It's just a technical term. It's just a term. Is the image of V1. It's just the target. Another word is image or target. It's the vector that F sends V1. Okay, well, let's see. Let's choose, let W be any vector. Let W be any vector in W. Now we want to show that this vector in W, right? Let's see what we want to say. We want to show that first. We want to show how would we show that WI. We've got these images here. How do we show? We want to show that these to be a basis. These vectors here. Let's see. Okay, to show. I've jumped the gun a little bit. To show that that F of V1, F of V2, up to F of Vn, to show that this is a basis, right? We have to show that they span the space. We must show that they span the space and are linearly independent, right? So we want to show that they span the space and are linearly independent, because then they would form a basis of W. Okay, well, to span the space, we go back here. This is what I was jumping the gun on. We want to let W be any vector here, and we need to show that it can be written as a linear combination of these ones, because it would span this. Because then, if I choose any vector here, and if I can write a linear combination of these, then it's going to then these vectors would span the space, right? So I choose a vector W, and I use the property that it is on that F is onto to say there is some vector V that W is the image of. For any vector W, there's got to be a V because F is onto, right? F is onto means for any vector in the codomain, I've got to have a vector in the domain that maps to it. So you got to get straight here. There's two different, there's the map properties onto and one-to-one, and then there's the vector space properties spanning the space and linearly independent that come. And so you've got sort of some concepts to juggle to sort of keep in view. Now, because V is in the domain, because the vectors V1, V2, and V up to Vn form a basis, we can write this as f of AV1 plus BV2 plus say X Vn, right? I can write this vector V, it's got to be a linear combination. I've got to be able to write it in as a linear combination of the vectors of V. This is true because the V1 to Vn form a basis of V, right? So being a basis of V, I can take any vector in V and expand it. Okay, now I want to use, so that's the reason because I can go from here to here because F is onto. I can go from here to here because the V's form a basis of V. Now I can use the fact that F is linear to write this as A F of V1 plus B F of V2 plus plus X F of Vn. This is due to F is linear, right? Now, what this means is, though, that W here equals a linear combination of the images of the original vectors, right? F of V1, F of V2, F of Vn. Therefore, right away, we have just shown that that the set, say, D of F of V1, F of V2, F of Vn span W, because I chose any W, use that F is onto to write it as the image of some linear combination of basis vectors in V, then use linearity to sort of transport that over to W, and I can see that these, so the images of the basis vectors in V span the space in W. Does that, hopefully the value of this is you sort of see how the concept, we're using the concepts directly just as concepts, so it helps you to sort of become familiar with those concepts. Now, if this set is linearly independent, we have to show this set is linearly independent because then it will be a basis, right? So let's, to show that these vectors are linearly independent, we have to show D is made of linearly independent vectors. Okay, now if it's made of linearly independent vectors, how do we know? Well, we have to show, I take some linear combination like R V1 plus S F of V2 plus the same kind of thing, and then say X F of Vn equals the zero vector in W, right? So I have to show that suppose this is true, I have to show that RS, all the coefficients X are equal to zero, right? Because that would show they're linearly independent. There's no way to trade them off against one another. So I have to show, so to do that, I So I have to, this is like a conditional, it's sort of like I'm saying, if this F, any linear combination equals 0, then all the coefficients are zero. Then it will be linearly independent. So let's suppose that this is true. F of V1, R times F of V1 plus S times F of V2 plus T times F of V3 plus plus X F of Vn equals the zero vector in W, right? Well, now what we're going to use is we're going to use the linear property up backwards. We're going to say, okay, well, this is a linear combination that's the right-hand side of this thing here. See, we went here, we sort of went from F of this back to the linear combination. We can say due to linearity, this is the same thing as F of R V1 plus S V2 plus T V3 plus X Vn that equals 0. So I've just rewritten this to say that because of linearity, because F is linear, I know that that's true. I can just sort of change it. Now, there's a theorem that says that, oh, well, here's the point. We know, okay. We showed earlier, last time, we showed that F of the zero vector in V equals the zero vector in W. Remember, what I can do is I can say, okay, well, here's F of the zero vector in V equals F of say 0 times the zero vector in V, because zero vector is the only vector that I can sort of peel off a 0 from and it won't change it, right? If I had like 1 here, I couldn't. It would annihilate. So 0 doesn't annihilate the zero vector because it's already 0. Well, I can apply linearity of this to say this is equal to 0 times F of the zero vector. But this 0 times any vector in W is equal to the 0 in W. So I end up with 0 always getting mapped to this. Okay, now here's where I can use the fact that F is 1 to 1. So since F is 1 to 1, remember, we're assuming that F is both 1 to 1 and onto. We've used the fact that F is onto, but we haven't used the fact it's 1 to 1. Because F is 1 to 1, I can't have this vector going to 0W and this vector going to 0. I can't have this two vectors, different vectors going to the 0 and W. So they must be the same one. In other words, if the images are the same, right? If it's 1 to 1, I can't have this. The only way that I can do it is if V1, if I choose two vectors, V1 and V2, and their images are the same, which they are here, then they're really the same vector. So I know that R V1 plus S V2 plus T V3 plus X Vn equals the 0 vector in V. So I used the fact that it's 1 to 1 to say that this 0 vector has to equal this linear combination. And then with the goal here, I want to show that this up here, that these vectors up here are linearly independent. So I'm supposing this is 0, and I've moved that back to saying to an expression in V. Now it turns out because the V's are linearly independent themselves. Why? Because V is a basis. We started off saying the V's are a basis. So that means they're linearly independent. That means that R equals S. Therefore, R equals S equals T equals X equals 0. the only way this could happen is if all the coefficients are zero. So that we got this from the fact that the V's are a basis, but then that's the condition that the F of V's are linearly independent. So because the V's are linearly independent, we know the F of V's are linearly independent. That's what F being linear and one-to-one and onto meant. So therefore, D equals F of V1, F of V2, F of Vn is both spans W and is made of linearly independent vectors. Okay, that means that D is a basis. The set here, D is a basis of W. So we've shown that the images of the basis vectors in V form a basis of W. Okay, so we know that the dimension of W equals the number of vectors in D. Well, how many vectors are there here? Right? Could it be that any of these vectors are, we have n vectors here, right? And there's not, we have n vectors, but then we can't write, none of these could be, the only way that the dimension of D could be less than n, we've got n vectors here, but the only way that they could be less than n would be if some of these were equal, right? So if you had F, but if you had F of V, say I, equal F of Vj, right? If this were true, if any of these were equal, well, that would imply, right? Because F is one to one. The images here would be the same. That would imply that Vi equals Vj. So if Vi and V, if I is not equal to J, if these, if Vi is not equal to Vj, then they can't happen, because if F of V1 equals that, because F is one to one, then Vi has to equal Vj. So none of these can be equal, because if any of these were equal, that would mean the two of the vectors were the same, and they would be linearly dependent. So we cannot. That means that this all means that the size of D equals n. Therefore, the dimension of V equals the dimension of W. So we've shown that if you have an isomorphism, the vectors have to be the same space. Now, I'm not going to go through in this much detail. I'm not going to go through and show. You can turn it around and say, if the dimension of V equals the dimension of W, then you can show that there is an isomorphism between V and W. Basically, what you do is you can, if you want, it's in a text, but if you say, well, if the dimension of two spaces are the same, that means they'd have this. You could choose a basis of V and a basis of W, and you know they have the same number of vectors. And then we could map like each of the vectors in V to W, basis vectors, and then form. We haven't done this yet, so that's why I'm not going to do this right now. That you can then show that there's a linear map with based on this thing where I take V1 to W1, V2 to W2, so I can construct an isomorphism using this, and then you can show that because they're both bases, what you've constructed is both one-to-one and onto, and linear, so you know you've constructed an isomorphism. So that's a little, so that what we did this way, so basically the result is this theorem at the end for isomorph, this is sort of the big consequence for isomorphisms. Let's see. If two spaces are isomorphic, then they have the same dimension. And here's, we just went over this, what we just went over is on this page here in sort of compressed form. Okay, now the other way that I just mentioned is if the spaces have the same dimension, they are isomorphic. Being isomorphic means there is an isomorphism. So what that means is that all the vector spaces divide up into isomorphism classes. You can sort of divide it's like all the spaces that have the same dimension, and there's going to be an isomorphism. And isomorphism means essentially they're the same thing, because I can take any vector, any linear combination of one, and make an image of a linear combination of the other. In particular, I can do this between, here's sort of any m-dimensional vector space is isomorphic to R to the n if and only if m equals n. So I can take any vector space of dimension, say m, like dimension 10, and it's going to be isomorphic to R to the 10. So all vector spaces are isomorphic to some set of column vectors. That's why your intuition that you want to convert everything to column vectors is okay, despite the fact that I've resisted you doing that, because they're isomorphic. So, but the point is that it's something you have to show, not something that's like obvious or interpretive, so that it means that you can look at all finite dimensional vector spaces, and you've got like the ones that are one-dimensional, two-dimensional, and you can choose the R to the n as sort of like the paradigm case of a dimension 2 vector space. So if you know about R2, two-component column vectors, you know about all two-dimensional vector spaces. They're really the same thing. They're like different avatars, different images of the same structure. So that means that instead of this huge thing of like all these different kinds of vector spaces, no matter where they come from, you already know about them because you know about column vectors. So you can take any problem that comes up in nature or some subject like economics or graphics and always transport it, convert it over to stuff with column vectors. So it's a useful, so that's what you get from, this whole idea of isomorphisms. It's as good as far as it goes, but that's not the main sort of topic, but that's sort of the end of a story.